So, how do we know about something we can't see? How can we possibly begin to understand the nature of a universe that is largely hidden from our direct observation? It seems like an impossible task, doesn't it? Like trying to map an ocean floor without being able to dive beneath the surface. That's the adventure we're about to embark on, a journey into the unknown, a quest to unveil the secrets of the cosmos. We're going to push the boundaries of our knowledge and explore the very limits of what we can perceive. It's a story of cosmic detective work, piecing together clues from the faintest signals, analyzing subtle patterns in the data, and using our ingenuity to infer the existence of things we can't directly observe. Watching galaxies spin, observing their movements and how they interact with each other, searching for anomalies that might betray the presence of unseen forces, measuring ancient starlight, dissecting the light that has traveled billions of years across the universe to reveal the composition and history of distant stars and galaxies, and mapping the afterglow of the Big Bang, studying the cosmic microwave background, the faint echo of the universe's birth to understand the conditions that gave rise to everything we see today. We're about to journey into the invisible universe, a realm of dark matter and dark energy where the rules of physics seem to bend and the familiar landmarks of our cosmic neighborhood fade away. To explore the shadows and understand the unseen forces that govern everything. To grapple with the mysteries of dark matter and dark energy, and to try to understand their role in shaping the universe we inhabit. It's a journey that challenges our very understanding of reality. It forces us to confront the limitations of our senses and to question the assumptions that underpin our scientific models. So let's begin. Let's embark on this incredible adventure together and see what wonders and mysteries await us in the depths of the invisible universe.
This is the most humbling discovery in science. The realization that our understanding of the universe is so incomplete that we are only just beginning to scratch the surface of cosmic knowledge. We've spent centuries peering deeper into space, building ever more powerful telescopes and developing sophisticated techniques to probe the cosmos, only to realize we're seeing just a sliver of reality, that the universe is far more vast and complex than we ever imagined. The universe is dominated by two mysterious components, dark matter and dark energy. These enigmatic entities make up the vast majority of the cosmos, yet we know very little about them. They don't shine or reflect light, making them incredibly difficult to detect. They are invisible to our telescopes and our eyes, but their presence shapes galaxies and the fate of the cosmos. They influence the way galaxies form and evolve, and they drive the accelerating expansion of the universe.
Aye, it certainly does. The influence of these unseen forces is undeniable, even if their nature remains a mystery. But all of it, every star and galaxy, is only the tip of a cosmic iceberg, a small, visible fraction of a much larger, hidden reality. The visible universe, everything we can detect with our most powerful instruments, is less than 5% of what exists. It's a humbling thought, isn't it? The rest, a staggering 95%, is invisible to us, a vast, hidden realm of dark matter and dark energy that we are only just beginning to explore.
Look up at the night sky. Take a moment to contemplate the vastness of space and the countless stars that twinkle in the darkness. What you see, stars, planets, galaxies, all the familiar objects of the cosmos, is just a tiny fraction of what's actually out there, a mere glimpse of the true scale and complexity of the universe.
Imagine a sea of particles constantly flowing around us, through us, and yet completely unseen. These aren't your everyday atoms. They're something far more elusive. We call them WIMPs, weakly interacting massive particles, and they could be streaming through us right now, an invisible cosmic tide. These WIMPs are invisible and undetectable except by their gravity. They warp the fabric of space-time, creating subtle gravitational ripples that betray their presence. It's like feeling a phantom weight, an unseen hand guiding the movements of galaxies. They're massive, far heavier than the particles we're familiar with. Think of them as cosmic heavyweights, silently influencing the universe on a grand scale. But despite their mass, they interact so weakly with ordinary matter that they're nearly impossible to catch. It's like trying to grab smoke with your bare hands. They slip right through. Scientists are building incredibly sensitive detectors, deep underground, shielded from all other interference, just to try and snag one of these elusive particles. Finding just one would be a Nobel-worthy discovery, a monumental achievement in our understanding of the universe. It would open up a whole new realm of physics, revealing secrets hidden for billions of years. It would be confirming that the universe is even stranger, more mysterious and more wonderful than we ever imagined. It would force us to rewrite our textbooks and rethink everything we thought we knew about the cosmos.
So, what is dark matter made of? What are these mysterious particles that make up such a significant portion of the universe? We know it's not ordinary matter, the stuff that makes up stars, planets, and us. It's not hiding in the form of dead stars, remnants of supernovae explosions scattered across the galaxies, and cold gas, vast clouds of hydrogen and helium drifting through space can't account for what we see. The gravitational effects of dark matter are far too strong to be explained by these ordinary sources. Scientists strongly suspect it's a new kind of particle, something beyond our current understanding. It's not part of our standard model of physics, the framework that describes all the known particles and forces in the universe. This means dark matter represents a fundamental gap in our knowledge, a missing piece of the cosmic puzzle. These hypothetical particles are called WIMPs, weakly interacting massive particles. The name itself hints at their elusive nature.
Imagine tossing glowing marbles in a dark room. If they curve around invisible objects, their paths subtly altered by an unseen force, you know something's there. Even if you can't see it directly, you can infer its presence by its effect on the things you see. That's essentially how astronomers detect dark matter, indirectly by observing its gravitational influence. They do this by watching stars and galaxies move under its gravitational pull, observing how their orbits are affected by this unseen mass. The speed at which galaxies rotate, for example, suggests there's far more mass present than we can account for with visible matter alone.
Let's start with dark matter, this mysterious substance that makes up a significant portion of the universe. It's dark because it doesn't emit or interact with light or any other form of electromagnetic radiation. It's completely invisible to our telescopes. It's matter because it has mass and exerts a gravitational pull, influencing the movement of galaxies and the structure of the cosmos. If you held a lump of it, hypothetically speaking, of course, you wouldn't see or feel it. It would be completely undetectable to your senses. Light would pass right through it as if it weren't even there. It's a truly bizarre and enigmatic substance. The story of the universe is one of constant struggle, a cosmic tug-of-war between opposing forces. Gravity, the familiar force that binds matter together, has always been thought to be the dominant player. But a baffling discovery revealed that something else was at play, something counteracting gravity on the grandest scale. This mysterious force is pushing space itself apart, driving galaxies further and further away from each other at an ever-increasing rate. It's as if the very fabric of the cosmos is being stretched and pulled in all directions. Scientists, initially perplexed by this phenomenon, eventually gave it a name: dark energy. This term reflects not only our ignorance about its true nature, but also its profound impact on the universe. Unlike dark matter, which clumps together and exerts gravitational pull, dark energy is believed to be a fundamental property of space itself, an intrinsic energy woven into the very fabric of the cosmos. It's not concentrated in specific locations, but rather spread smoothly and uniformly throughout the universe, acting as a constant pressure pushing everything outward. And here's the truly mind-boggling part. This dark energy is not just constant, it's growing stronger as the universe expands, fueling an ever-accelerating expansion. It's a runaway process, a self-perpetuating cycle where the more the universe expands, the more dark energy there is, and the faster it expands. This has profound implications for the fate of everything, raising fundamental questions about the ultimate destiny of the cosmos and our place within it.
But in the late 1990s, a revolution began to unfold in the field of cosmology. Astronomers, meticulously measuring the distances and velocities of distant supernovae, those brilliant stellar explosions that mark the death of massive stars, found the opposite of what they expected. Instead of slowing down, the universe's expansion is speeding up, accelerating at an astonishing rate. It's as if you threw a ball up in the air, and instead of slowing down and falling back to Earth, the ball is accelerating away from you, defying gravity. This acceleration is powered by something unknown, something we can't directly see or touch.
Think of throwing a ball up into the air. Gravity, the force we all experience every day, slows it down, eventually bringing it to a stop before it falls back down. The universe, too, filled with matter and energy, should be slowing as it expands, its expansion gradually decelerating under the relentless pull of gravity.
If dark matter, the invisible substance that makes up the majority of the universe's mass, holds the universe together through its gravitational influence, dark energy is pushing it apart, acting as a repulsive force that counteracts gravity on the largest scales. For decades, based on our understanding of gravity and the composition of the universe, astronomers thought gravity would eventually slow the universe's expansion, maybe even reverse it, leading to a big crunch where the universe collapses back in on itself. The only explanation galaxies are surrounded by massive invisible halos of dark matter. Rubin's work proved Zwicky's missing mass was real.
Decades later, Vera Rubin found that stars at the edges of galaxies were moving as fast as those near the center, defying gravity's rules.
The cluster should have flown apart, but something unseen, what Zwicky called dark matter, was holding it together.
The story of dark matter began in the 1930s, when Fritz Zwicky noticed galaxies in the Coma cluster were moving too fast to be held together by visible matter. This shocking result revealed the presence of dark energy, earning the teams the Nobel Prize.
Instead, the supernovae were fainter than expected, farther away than they should be. The universe's expansion was speeding up, not slowing down.
In the 1990s, two teams used these supernovae to measure how fast the universe was expanding. They expected to find the expansion slowing down.
These exploding stars are so bright and consistent that we can use them to map cosmic distances.
The discovery of dark energy came from measuring the universe's expansion using standard candles, type Ia supernovae. The oldest light in the universe, the cosmic microwave background, also reveals the fingerprints of dark matter and dark energy. The patterns in this ancient light match the amounts needed to form galaxies and explain the universe's shape. The numbers line up perfectly with what we see in supernovae and galaxy rotations.
The bullet cluster is a dramatic example. Visible matter slowed in a collision, but most mass, dark matter, passed through untouched.
When we measure the lensing, we find more mass than we can see, dark matter.
If we can't see or touch dark matter and dark energy, how do we know they're real? The evidence comes from many sources. One is gravitational lensing, massive objects bending light as predicted by Einstein. Dark matter pulls things together. Dark energy pushes them apart. The fate of the universe hangs in this cosmic tug-of-war, and right now dark energy is winning.
The largest slice, 68%, is dark energy, the force driving the universe's accelerated expansion.
The next biggest slice, about 27%, is dark matter, the invisible scaffolding that allowed galaxies and stars to form. Without it, we wouldn't exist.
Every story, every discovery, every atom we know is just a tiny sliver of reality.
When we add up all the evidence, we can draw a cosmic pie chart. Ordinary matter, everything we see, makes up less than 5% of the universe. Dark matter made our existence possible, providing the gravity to form galaxies and stars. Without it, the universe would be a featureless soup. The discovery of dark energy rewrote our understanding of the future. If it continues to dominate, galaxies will accelerate away, vanishing from view. The night sky will grow empty, and future civilizations may never know the universe was once full of galaxies. Dark matter and dark energy show us that our understanding is incomplete. They point to new physics waiting to be discovered. They are clues to the next great scientific revolution.
Why should we care about these invisible substances? Because they answer the biggest questions. Where did we come from? Where are we going? The search pushes technology and imagination to their limits. We've discovered that the universe we see is just a faint glimmer in a vast, unseen cosmos. The answers, when they come, will reshape our understanding of everything. The dark is not empty. It's full of secrets waiting to be discovered.
So where do we go from here? The quest to understand dark matter and dark energy is just beginning. For dark matter, scientists are building ultra-sensitive detectors deep underground, hoping to catch a single WIMP. Others try to create dark matter at the Large Hadron Collider, searching for missing energy in high-speed collisions. For dark energy, astronomers are building new telescopes to map the universe and track its expansion in detail.